Okay, so in this video we will be going over linear approximation of a function, and for that we will make use of the following. Whenever we have a complicated function f of x, it can be a trigonometric function or any function of any sort. There's a very convenient way to approximate this function, and it is the following. F of a, so I will first give you guys the linear approximation formula, and then we can discuss what is the meaning of this this approximation, f prime of a. There you go. So this is an approximation of our function f of x near, so let me write that down, approximation of f of x near a point near x equals a. So let's think about what that all means. So suppose that you have this function, and maybe it might take different shape over there, and suppose that our goal is to approximate its value near the point A. So what we will do is the following. So we have, suppose that this is a point A, and near that point we have that other point X. All right, so this is the x-axis, and this is our function f of x. So what we can do is the following, again using the tangent line. So we evaluate the derivative of our function at that point, and it will give us this tangent line if we were to calculate it. But there's yet another way we can do evaluate the value of that. So this function will end up being a so the slope of this function, slope equals f prime of a, and it turns out that we can use the following trick. So our goal is to approximate a value for f of x, this value basically. But, so this is f of x. We can do the following approximation. So if you zoom into this picture, we just suddenly realize that if you consider this triangle, if you want, a right triangle for that matter, we can instead look at the tangent line and look at this value instead of calculating that value. Do you guys see? So the error term is extremely small, namely this distance over here. So this is the error term, and that would be a good approximation. And so what I can do is, if I focus my attention on that right triangle, I can calculate the slope of that triangle in two different ways basically. First, as the derivative of the function, the original function f of x. So as a result, let me just go ahead and do that. Actually, let's just use this key here. All right, there you go. So on the one hand, okay, so let's write out the slope. Slope on the one hand is equal to f prime of a, because that's where we are calculating the slope. But at the same time, on inside that yellow right triangle, it would be rise over run. So when you look at the rise, that would be well, because this distance here is f of a, so it would be just f of x minus f of a, f of x minus f of a, all divided by this distance, which is really x minus a. There you go, x minus a. Now we can go ahead and take cross multiplication, so that would imply that x minus a times f prime of a is simply equal to f of x minus f of a. Well, actually, this is not an equal sign, right? This is just an approximation, so I need to clarify that. So let's put an approximate sign over there. And finally, we can move that f of a to the right left-hand side, and that will give us exactly what we needed, right? So f of a plus x minus a times f prime of a is approximately equal to f of x, and that's exactly what we needed to show, right? So let me go ahead and highlight this. So that was the formula that we wanted to show, and there it came. So we need to say a few words about this approximation, I guess. So this is an approximate value approximation, and it will become a better approximation if that point x is nearby the value of a. As x gets closer and closer to, let's write that down, as x gets closer and closer to that point a, then the value of f of x will get closer and closer to the value of f of a. And as a result, implying that the error term, which is f of x minus f of a, will get closer and closer to 0 if you want. So that's the logic behind linear approximation. It turned out to be a huge idea, especially during the 1940s and 50s, where especially with combining these ideas with matrix algebra, linear algebra, you can come up with some very strong optimization algorithms. All right, so just as a let's finish this lecture with a quick example. For instance, earlier with our Newton method, we were able to evaluate root 2, approximate value of root 2 up to 9 decimal places of accuracy. Let's see if we can make that same calculation, 1.414 and so on. I want exactly 9 decimal places. All right, so what we will do in this example will be the following. This time, instead of considering a polynomial for which root 2 will be a root, we will directly consider f of x equals square root of x. In that sense, we are trying to calculate f of 2 to be exact, right? So and that's it. So what we will do is we will start with an approximate point. I think when we did the during the Newton method, we did use 1.5 as our initial starting point. It will be pretty similar to that. We need to start with a nearby point, and then based on that point, we will try to get closer and closer values for our function. And that's pretty much what we can do. So for instance, if I were to calculate the value of our approximation, okay, let's do it. Square root of 2 will end up being equal to, well, sorry, approximately, I should say, approximately equal to, depending on how close our initial guess is, 1.5, right? So that's, or let's just do it in 2 steps. So it is, remember that it was just f of a plus x minus a, f prime of a. So that means this is root 2 is approximately equal to, so first we need to plug in the value 1.5 into our function, because that's so choose a equals 1.5. We think that that's a good enough approximation. So we need the square root of 1.5. That's our function. F is our function. And then 1.5 minus a. Well, the a in this case is a 2, right? So that's what we need to plug in. The value that, 2 is the value that we want to compute, and a is 1.5. Sorry for that. 2 minus 1.5. And finally, f prime of a. Let's rewrite this nicely. Okay, there we go. So we also need the derivative of this function that let me quickly also make that calculation over here. F prime, if you take the derivative of square root x, or you use a software, it is just 1 over 2 square root x. So therefore, I need to plug in within, the a is 1.5, so plug in 1.5 over there, we get 1 over 2 square root of 1.5. That's it. So that's our approximate value for root 2. Let's see how close we get. And in the second iteration, we will use that close value to estimate the value of root 2 even closer, right? So if we start with this, and I have a calculator in front of me, we will just see that, hold on, oops, sorry for that. So I have my calculator now. So on the one hand, we have square root of 1.5. Let's just go ahead and take that square root here. All right, so I have my calculator ready. 1.5, the square root of it is 1.2247, for instance, 1.22. Okay, let's have it like this. Plus, so 2 minus 1.5 is 0.5. And then 1 over 2 times square root 1.5, so just times 2, I guess. So that's 2.44, or maybe I should have, okay, let me just add one more digit of accuracy because it's extremely close call. Okay, there you go. All right, so now when you evaluate this as a first iteration, so this is approximately equal to, so let's check. Okay, I have my calculator. So we have 1 over 2.449 equals times 0.5 equals, so the second term here is 0.2, or actually let's do it one more step, 225 plus 0.204. All right, so 204, and as a result this came out as 1.225, 1.429, 1.429. Yeah, that was a really good call, right? We know that the correct answer is this. Okay, so now that we have this approximate value for square root of 2, which is, you might say, hey, this is okay answer, but it's not that close to 1.414, and what if we needed more decimal places of accuracy, right? So what we needed, that step, is to go one step further, and so linear approximation won't do it. Now we need a second degree approximation, and the second degree approximation will follow from the following. And this in general, these type of approximations are sometimes called Taylor approximations. Let me explain what that what the formula is, and then let's go over the meaning of such a formula. So if you want to evaluate the value of your function at the point x, which turns out to be very close to that point a, which is easier to evaluate, then what you can do is the following: x minus a f prime of a, so that's we did so far, plus now we need to add a second term yet, x minus a square, and then f double prime of a all divided by 2, actually to be more precise 2 factorial. So that will give you yet an additional approximation, which will be even better than the previous one. So this is approximately equal to. And it turns out that Taylor says that you can do even more than that. You can keep adding more terms of that fashion. So let me keep adding the terms. X minus a cubed f triple prime of a all divided by 3 factorial, which is 6. And then so on. So the more terms you add, obviously it will be more costly for you to get to the third or the fourth derivative of a function, and then make these calculations. So it will be more and more precise, plus an error term, right? So you should decide where to stop that sequence, basically. So going back to our problem at hand, so for an approximate value for root 2, so far by just using the first 2 terms, these 2 terms, we were able to get all the way up to a certain value. Let's just go ahead and write that out. So far we have 1.429. Okay, so we just write it out, 1.429, and then plus, let's see what happens if we were to add one more term to that. So let's have that one more term, this one. So let's see if we will get an even yet more accurate result. So first what I need is, sorry for that. So what I need is the second derivative of our function, and then we will evaluate it at the desired point. Okay, so let's go ahead and calculate. So our function was f of x, oops, let's write it here. F of x equals square root x, right? So after the first derivative, we got 1 over 2 root x, and if we were to take yet another derivative of that function, actually let's just write it as x to the minus 1/2, so it would end up being a minus 1/4 x to the minus 3/2. All right, so therefore now plugging in the value a onto our function, and then so what we will get is the following. So our point of interest is 2, which is so what was our point, that original point? 1.5, yes. So our point, so the point 2 that we are evaluating is close to 1.5, right? So I will just go ahead and write 1.5 minus 2 square, right? And then we have f double prime of a, so just plug in the value into that very nasty looking expression. So let me first divide by 2, 1/2, and then we have minus 1/4, so this is a multiplication. Replace x with that value 2. Sorry, it should be the other way around, 2 minus. It doesn't matter because we are gonna square in the end. So so plugging in the value of 2, I should say, so we get just like we did over here, right? So if you just go back, that's that was yes. So So yeah, our value of a is 1.5, and so basically our calculation of x is based on that value of a. So yeah, so x minus 2 minus 1.5, and then we have substituting 1.5 over here, which is pretty nasty. 1 over, okay, let me just do it like this, the 1.5 cubed and then the square root of that, right? So that's pretty much it. So this is the adjustment that I need to make, and hopefully with that adjustment my answer will be closer. I can already see, and there will still be an error term, and that's why we have this approximation, so no need to put an error term. So luckily this iteration will give us an even closer result. So 0.5 square is 0.25. And then this product, actually we will end up with a minus sign here, right? Because the 1 over 4 has a minus in front of it. So we have a 1 over 8, not 16, 8. And then 1 over the square root of 1.5 cubed. And let me go ahead and using my scientific calculator, 1.5 cubed gives me 3.375. Now taking the square root of that gives me 1.8371. Okay, so, and then I need to multiply it by 8. I have the denominator, then take the reciprocal. So I'm just basically doing the calculations right away on the spot. Okay, there we go. And then finally multiplying it by 0.25. Okay, so the adjustment term, so this whole thing came out as 0.017. All right, so this whole thing is 0.017. So therefore, the new approximate value is 1.429 minus 0.017, and that is equal to, let me just go ahead and do the calculation, plus 1.429, 1.412. Wow, so this is really nice now, right? So do you guys agree that compare this with this? Now this is way better, because remember that root 2 was 1.414. Now in the first step we got 1.429, in the second step 1.412, and if we included the next term in line, we will get yet a way better, much better approximation. So yeah, that solves this example. So I will provide yet another example in my next video.